welcome to the 7 o'clock news. Tonight we have an exclusive look at how first year students at the University of Birmingham have managed to find a solution to a serious problem. One proposed by the National Agricultural Mathematical Modelling Institute, also known as NAMI. The problem is, on a given area of ground surface, how many plants are to be planted to achieve the maximum yield? This may not appear to be pivotal to the development of common crop plants in the UK. However, it affects farmers, suppliers and grocery stores across the nation. For more on the situation, we go over to our correspondent in the field. Jeff, what more can you tell us?
Good evening. Yes, I am stood in the field, one where this very problem affects how much plant material is produced from planting to harvest. The solution may seem obvious that planting as many crops as possible will generate the largest yield. However, too many crops can result in there not being enough nutrients needed for effective growth. This results in crops being weaker, which means it takes longer for plants to reach maximum yield. For the most effective growth, there needs to be a balance between growing enough crops to get high yield, but not too many that will inhibit crop growth.
That does sound like a serious problem for farmers across the UK. So let's see how students at the University of Birmingham have tackled the situation.
For our model to be valid, we've taken some certain assumptions. Each plant receives an equal amount of sunlight, mineral ions, water, and space. All crops survive the harvest. Growth rate and number of plants have a linear relationship. All crops have equal growth rate at all times. At planting, each barley weighs 1/18 of a gram. We got this from our website. Size of the plot is constant. And finally, the barley has a carrying capacity of 100, and we'll explain this later.
To begin with, our group knew that we wanted to create a differential equation to express the growth of a plant from planting to harvest. The differential equation we came up with was this. This works because it expresses the rate of change of yield in relation to the yield because they are both dependent on each other. This expression works because when little y is small, then the whole expression tends to k, and when little y approaches capital Y, which is our carrying capacity, then this approaches 0. And little y is our yield, t is our time, and k is a growth rate constant. Solving this, we find this equation where capital A is just a constant. Okay, so now we can note that little y equals NW. So the yield can be expressed in terms of the number of plants n times the weight of one plant. We know that the weight of one plant varies with time, so we can set up a differential equation, as shown here, dw over dt equals LW, where L is just a constant. Solving this, we find W equals ME to the LT, where M is again just a constant. Substituting in T equals 0, we find that W equals M, and from now on we'll call this M W0 because it is the weight at time 0 of the plant. So substituting in y equals NW into equation 1, we find this equation, and then substituting in t equals 0 and w equals w0, which are our initial conditions, we find that capital A equals NW0 over capital Y minus NW0. Substituting this into equation 1 to eliminate A gives little y equals this expression. Now, using the graph of yield against time from the data, we can set capital Y, our carrying capacity or maximum yield, to be 100. And from research using the internet, we find that W0, the weight of a plant at the very start when t equals 0, basically the weight of the seed, is 1 over 18 grams. So substituting these in, we find little y equals this expression. Now, we can rearrange this equation for k, which gives us this, and then using t as 6 weeks, using the data we've been given, we can also plot a graph again, which will be approximately a straight line. Finding the y-intercept and the gradient gives us an equation in k and n that is linear, as shown, k equals -1 over 496n plus 0.8. Substituting this into equation 2, so this one, we find this equation, which basically means we've gotten rid of both k and capital A. So now we want to try and get an equation in y and n. Before we can do this, however, we should validate the model, and we can do this by using the data we've been given to substitute in different values of n and t, and finding the yield and comparing it using graphs and overlaying our model data compared to the experimental data we were given. Then substituting in t equals 10, because we will only really want to let the plants grow for 10 weeks, we find that yield equals this expression. This means we now have an equation in terms of just yield and the number of plants, and graphing this enables us to find the optimum number of plants we should grow. As you can see from the graph here, the optimum number of plants we should grow is approximately 51.
To conclude, from our graph of y against n, we have found that the optimal number of plants per plot is approximately 51, and this will produce a maximum yield of approximately 97 over the set time period of 10 weeks.
Well, that is brilliant. And as you can see, this once serious problem has been dealt with effectively, and farmers can remain calm, as they will be maximising their yield if the number of crops they plant in any given area is worked out using this model. Isn't that right, Jeff?
Yes, that is right, and NAMI should also feel confident that yields will be at their maximum, ensuring the largest profit when about 51 crops are planted per plot. Back to you in the studio. Is that Theresa May?